Welcome to the deep dive. Today, we're going to plunge headfirst into the world of quantum mechanics. We've got a fascinating article here on quantum objects and states.
Cool.
Think of it as our guidebook to this realm where the usual rules of reality just don't apply.
You're in for a wild ride.
Yeah.
We're talking particles that act like waves,
Whoa.
fundamental limits on what we can know,
Okay.
and even a phenomenon that spooked Einstein himself.
Intriguing is an understatement. So before we get to the really weird stuff, can you give us the big picture? Why should we care about quantum mechanics in the first place?
Well, quantum mechanics is how we understand the universe at its most fundamental level. Think atoms, photons, electrons, the building blocks of absolutely everything.
Got it.
And it's not just theoretical. Quantum mechanics underpins so much of modern technology.
So no lasers or smartphones without quantum mechanics. That's a pretty big deal.
Exactly. But here's where it gets really interesting and challenging. Quantum mechanics breaks from our everyday experience. As the article points out, things aren't so clear-cut in the quantum world. We're not dealing with certainties, but with probabilities.
Okay, let's unpack this idea of quantum objects. What exactly are they?
They're the fundamental building blocks we just mentioned, electrons, photons, atoms, but they don't behave like the solid, predictable objects we're used to. Imagine trying to play pool with billiard balls that could also ripple like water.
That's a pretty mind-bending image, and that's what this whole wave-particle duality thing is all about, right?
Precisely. Quantum objects can exhibit properties of both particles and waves, depending on how we observe them.
Right.
And to grasp this, we need to introduce the concept of the wave function.
All right. Hit me with it. What's a wave function?
Think of it like a heat map.
Okay.
A mathematical description that shows us the probability of finding a quantum object at a particular location.
Got it.
In some areas, the heat is higher, meaning there's a greater chance of finding the particle there.
Okay.
In other areas, it's cooler, meaning the probability is lower.
So instead of knowing for sure where an electron is, we have this wave function telling us where it's more likely to be.
Exactly.
That's kind of trippy, right?
It is, and it's one of the key things that distinguishes quantum mechanics from classical physics. We can't pin down the exact location of a quantum object with absolute certainty.
So we've got these quantum objects that are both wave and particle.
Right.
Their location is a matter of probability.
Yep.
And they seem to have some pretty unique properties. The article calls out 3 in particular, almost like quantum superpowers.
It does, and these properties are what make quantum mechanics so fascinating and powerful.
Let's dive into those superpowers. What's the first one on the list?
First up is the idea of discrete energy levels.
Okay.
Think of it like a staircase. A quantum object can only exist at specific energy levels.
Got it.
Like stepping on individual stairs.
Right.
It can't be halfway between steps. Unlike in classical physics where energy can change smoothly, like walking up a ramp.
Okay, so no energy ramps for these quantum objects, only specific energy steps. What's the implication of that?
Well, it explains why atoms emit light at very specific colors. For example, when an electron jumps from a higher energy level to a lower one, it releases a photon of light.
Yeah.
The color of that light corresponds directly to the energy difference between the two steps.
So that's why we see those distinct colors when we look at things like neon signs. It's all about those quantum energy jumps.
It is.
What's the next superpower we need to know about?
Next up is the Heisenberg uncertainty principle.
Okay.
And this one's a real head-scratcher.
Right.
It says that the more precisely we know a quantum object's position, the less we can know about its momentum, or vice versa.
Wait a minute, you're telling me there's a fundamental limit on what we can know about these particles? Not just that our instruments aren't good enough, but that it's baked into the fabric of reality?
Exactly. This isn't a measurement problem.
Yeah.
It's a core principle of quantum mechanics.
God.
And it's not just position and momentum.
Okay.
Other pairs of properties have this same uncertainty relationship.
So it's like a cosmic game of hide and seek.
Yeah.
If we try to pinpoint an electron's location, its momentum becomes blurry. And if we nail down its momentum, we lose track of where it is. Okay, I'm ready for superpower number 3.
Okay.
The article mentioned this wave-particle duality thing again, but with an experiment, the double slit experiment.
Ah, yes. The double slit experiment is where things get really strange. And it provides a classic demonstration of this wave-particle duality.
Right.
Imagine we fire a beam of electrons at a barrier with 2 slits.
Got it.
Behind the barrier,
yeah,
there's a screen that detects where the electrons land.
Okay, I'm picturing it.
Okay.
So if electrons are particles, I'd expect to see 2 distinct bands on the screen, right? Like they went through one slit or the other.
That's what you'd think based on our everyday intuition.
Right.
But that's not what happens.
Oh.
Instead, what you see on the screen is an interference pattern. A pattern of bright and dark bands.
Okay.
Just like you'd see with waves.
An interference pattern, like why waves?
But we're shooting particles, right?
Right. And that's the mind-blowing part. It's as if each electron is going through both slits simultaneously, interfering with itself like a wave. But when they hit the screen, they're detected as individual particles.
So they're somehow behaving as both waves and particles at the same time. This is definitely stretching my brain.
It is. And it's one of the most profound and puzzling aspects of quantum mechanics.
Okay, so we're dealing with these incredibly strange quantum objects.
Yeah.
And the article explains that we need special ways to describe them.
That's right. It outlines 2 main models.
Okay.
The particle model and the field model.
Got it.
The particle model is helpful for visualizing things like electrons orbiting an atom, treating them as distinct points.
Like tiny planets orbiting a tiny sun. Exactly. But then there's the field model, which is more powerful when we're considering interactions and forces.
Gotcha.
Think of it like a vast invisible ocean. Particles pop in and out of existence as excitations of this field.
Whoa.
Like ripples on the surface of the water.
Whoa. Particles popping in and out of existence. It just keeps getting more and more surreal.
It does, but that's the beauty of quantum mechanics. The article is clear that we need both models to truly understand what's going on.
Right.
It's not one or the other, it's both.
All right, so we've got these models, but we still need a language to talk about the states these quantum objects are in. The article hints that things are about to get a bit more abstract here.
It does get more abstract, but stick with us. We've already touched on the wave function as a kind of heat map showing probability.
Right.
But it's actually much more than that. It's like a code that contains all the information we can possibly know about a quantum object.
So the wave function isn't just about location, it's the whole shebang. Everything we can know about a particle's state.
You got it. And then there's the Schrödinger equation. This is the big one, the central equation of quantum mechanics.
Okay.
It tells us how the wave function changes over time.
Right.
Like a set of instructions for how quantum systems evolve.
So if the wave function is the code,
yes,
the Schrödinger equation is the decoder ring, helping us understand how that code unfolds over time.
That's a great way to put it.
Yeah.
It's the key to understanding how quantum systems behave and change.
The article briefly mentions something called bracket notation.
Yeah.
But it sounds like that's a bit too deep for our dive today.
Yes, that's a more advanced mathematical formalism.
Okay.
It's fascinating.
Right.
But we'll save that for another time.
Okay, good to know. But we do need to talk about the different types of quantum states, and the article hinted that things get even weirder.
They do. We've got stationary states, which are stable energy levels.
Okay.
Like those in atoms.
Got it.
But then things get really interesting with superposition.
All right, I'm ready for more mind-bending concepts. What's superposition all about?
Well, remember how we said quantum objects can be both wave and particle?
Right.
Superposition takes that to another level.
Mm-hmm.
A quantum object can actually be in multiple states, A to 1C. It's not just one or the other.
Wait, you're saying a particle can be in multiple places at the same time? How is that even possible?
It's one of the most bizarre and counterintuitive aspects of quantum mechanics.
Yeah.
Think of it like a coin spinning in the air. It's both heads and tails until it lands.
So a particle is in this blurry, undefined state until we measure it.
Right.
And that's when it chooses one state or the other.
That's a great question.
Yeah.
And it leads to a lot of debate about the nature of measurement and reality in quantum mechanics.
Okay, I can see why this stuff keeps physicists up at night. But before we get too philosophical, there's one more state we need to talk about: entanglement. The article made it sound like this is where things got truly spooky, even for Einstein.
It is.
Yeah.
Entanglement is where two quantum objects get linked together in a way that defies our classical understanding of space and time.
Got it.
If we've measured the state of one entangled particle,
yeah,
we instantly know the state of the other.
Okay.
No matter how far apart they are.
Instantly. Like faster than the speed of light instantly.
Yeah.
That's what freaked Einstein out.
Exactly. He called it spooky action at a distance for a reason.
Right.
And it's not just theoretical. It's been experimentally verified countless times.
So if I measure one entangled particle here,
yeah,
I instantaneously know the state of its partner, even if it's on the other side of the galaxy.
That's right.
That's just wild.
It is, and it's one of the most profound and mind-bending concepts in all of science.
Okay, we've covered a lot of ground here. Quantum objects, wave-particle duality, the uncertainty principle, superposition, entanglement. It's clear why this stuff is so revolutionary. And I can see how all of this leads to those groundbreaking technologies I've been hearing so much about.
Absolutely. Quantum mechanics isn't just a bunch of weird theoretical ideas. It's driving incredible advancements in fields like computing, cryptography, and sensing.
That's a perfect segue to part 2 of our deep dive, where we'll explore those mind-blowing applications. But first, a quick break. Welcome back to the deep dive. In part 1, we took a deep dive into the strange and fascinating world of quantum objects and states.
Right.
Now we're shifting gears to explore how those very same concepts are powering some truly mind-blowing technologies.
It's amazing how these seemingly abstract ideas are now at the forefront of innovation, shaping the future in ways we're only beginning to understand.
Let's start with quantum computing.
Okay.
It's been touted as the next big thing with the potential to revolutionize just about everything. But honestly, it still feels a bit like science fiction to me. Can you break it down? What exactly makes quantum computing so different?
It all comes down to harnessing those quantum phenomena we were discussing earlier. Remember how classical computers rely on bits, which can be either a 0 or a 1?
Yeah, those binary digits that make up all our digital data.
Well, quantum computers use qubits.
Okay.
Qubits can be 0, 1, or R, both at the same time, thanks to superposition.
Okay, that superposition thing is back. So it's like having a bit that's both on and off simultaneously. How does that translate into actual computing power?
That's where the real magic happens.
Right.
By leveraging superposition, a quantum computer can perform multiple calculations at the same time.
Okay.
It's like having a massive parallel processing system all in one.
So instead of crunching through calculations one by one, a quantum computer explores a vast number of possibilities in parallel.
Yeah.
That sounds incredibly powerful.
It is.
But also really hard to wrap my head around.
It is mind-bending.
Yeah.
It's this quantum parallelism that gives quantum computers a massive speed advantage for certain types of problems. The article mentioned drug discovery as a potential game changer.
Right. I can see how being able to simulate complex molecules at that speed would revolutionize medicine. What else is on the horizon?
Well, the article also highlights material science.
Okay.
Quantum computers could help us design new materials with specific properties, leading to breakthroughs in energy storage, superconductivity, you name it.
So lighter, stronger materials, more efficient solar panels, maybe even room temperature superconductors, all thanks to quantum computers.
It's certainly a possibility.
Yeah.
And that's just the tip of the iceberg.
Wow.
Quantum computing could also transform fields like artificial intelligence, financial modeling, and even help us understand the universe at a deeper level.
Okay. I'm starting to grasp the potential here. But quantum computing isn't the only area where quantum mechanics is making waves, right? Yeah. The article also mentioned quantum cryptography.
It did.
Okay.
And it's a fascinating application of some of the spookier aspects of quantum mechanics.
Right.
Quantum cryptography leverages these principles to create communication systems that are virtually unhackable.
Yeah.
It's like having a secret code based on the laws of physics themselves.
Now that's got my attention. How does that work? Does it have something to do with those entangled particles we were talking about earlier?
You guessed it. Remember how we said that measuring one entangled particle instantly affects the other, no matter how far apart they are?
Yeah, that spooky action at a distance thing.
Well, you can use that to create a secret key that's shared between two parties.
Got it.
Since any attempt to eavesdrop on the communication would disrupt the entangled particles, the sender and receiver would immediately know if someone was trying to listen in.
That's brilliant. It's like having an alarm system that goes off if someone even tries to peek at your message. No more worrying about hackers cracking codes or stealing data.
That's the idea.
Wow.
And because the security is based on the laws of physics, it's incredibly robust.
Okay.
It's not about creating more complex algorithms.
Right.
It's about using the fundamental nature of reality to secure information.
Okay. Color me impressed.
Okay.
This is sounding less like science fiction and more like the future is already here. But before we move on, there was one more application. The article mentioned quantum sensing. What's that all about?
Quantum sensing is all about harnessing the exquisite sensitivity of quantum objects to make incredibly precise measurements.
Got it.
Think of it like having instruments that can detect the tiniest changes in magnetic fields, gravitational fields, and even time itself.
So we're talking about super-powered sensors that can detect things far beyond the capabilities of our current technology.
Exactly. It's like gaining new ways of perceiving the world around us. The article highlighted a few areas where quantum sensing could have a major impact.
Like what? Give me some examples that will really bring this home.
Well, imagine medical imaging. That can detect diseases at their earliest stages long before any symptoms appear. Or navigation systems that are so precise they can guide you through a dense forest or even underground with pinpoint accuracy.
Wow, that's incredible. It's like having a sixth sense that allows us to see things that were previously hidden from view.
That's a great way to put it.
Yeah.
And it goes even further. Quantum sensing could also revolutionize fields like geology, allowing us to map underground resources with unprecedented precision. Or imagine telescopes that can peer deeper into space than ever before, revealing new secrets about the cosmos.
Okay, my mind is officially blown again.
Yeah, sure.
So we've gone from these seemingly abstract concepts of quantum objects and states to real-world applications that could revolutionize everything from medicine and communication to our understanding of the universe itself.
It's a testament to the power of scientific exploration and how fundamental discoveries can lead to incredible technological advancements. And we're really just at the beginning of this quantum revolution.
That's both exciting and a little daunting, right? It makes you wonder what other incredible breakthroughs might be just around the corner.
It does. And that brings us to the final part of our deep dive. While we've seen the amazing potential of quantum mechanics, there are still many challenges and open questions that continue to puzzle scientists.
Okay, I'm ready to dive into those mysteries in part 3, but first, a quick break. Welcome back to the deep dive. We've explored the bizarre world of quantum objects and witnessed how they're driving incredible technological advancements. But as with any frontier, there are still mysteries that keep scientists scratching their heads.
You're absolutely right. Quantum mechanics is a powerful framework, but there are some fundamental questions we haven't fully answered. The article we've been discussing dives into a few of these challenges.
What kind of questions are we talking about? Are we talking about tweaking existing theories or something more fundamental?
In some cases, it's about pushing the boundaries of what we even know is possible. One of the biggest mysteries is how to reconcile quantum mechanics with our understanding of gravity. We have two incredibly successful theories: quantum mechanics for the very small, and general relativity for the very large.
But they don't seem to play nicely together, do they? It's like trying to fit square pegs into round holes.
That's a great analogy.
And
it's a problem.
Okay.
Because there are places in the universe where both gravity and quantum mechanics are at play, like black holes or the very early universe.
So we need some kind of new theory to bring these together.
We need a new theory, a theory of quantum gravity to fully describe what's happening in those extreme environments.
So this missing theory of quantum gravity, any promising leads on that front?
There are a few contenders, like string theory and loop quantum gravity, but they're incredibly complex and still very much under development. We're talking about rethinking our understanding of space and time itself.
Now that's a mind-boggling concept. But the article also mentioned another challenge, how quantum mechanics plays out in the large-scale world.
We see these strange quantum effects at the microscopic level. But what happens when we scale things up? Why don't we see things like superposition and entanglement in our everyday experience?
It makes you wonder, does a baseball also exhibit wave-particle duality? Does a cat really exist in a blurry state of being both alive and dead until we open the box? Like in that Schrodinger's cat thought experiment.
Exactly. That thought experiment highlights a fundamental question about measurement in quantum mechanics. Does the act of observing a quantum system force it to choose a state? Or is something else going on? These are the kinds of questions that keep physicists up at night.
It's enough to make you question the nature of reality itself. So what's next for quantum mechanics? What's on the horizon for this strange and powerful field?
Well, apart from those big theoretical questions, there are also practical challenges.
Oh.
We're still in the early stages of building quantum computers.
Yeah.
And they're incredibly complex and delicate.
Yep.
We need to find ways to scale them up.
Right.
Make them more reliable.
Yeah.
And figure out how to program them effectively.
It's like we've opened this amazing new toolbox, but we're still figuring out how to use all the tools.
Right.
It's exciting to think about what we might build once we master these quantum technologies.
Absolutely. We've seen how quantum mechanics has already led to incredible breakthroughs.
Right.
And there's no telling what the future holds.
Yeah.
One thing's for sure, we've only just begun to scratch the surface of this fascinating and potentially revolutionary field.
It's amazing to think that something as seemingly abstract as quantum mechanics could have such profound implications for our understanding of the universe and the technologies we create.
That's the beauty of science. It's a constant journey of discovery, pushing the boundaries of what we know and opening up new possibilities we could never have imagined.
And that, my friend, is why we dive deep into these topics to explore the unknown and unravel the mysteries of the universe. We've journeyed from the tiniest particles to the most mind-bending concepts, and hopefully you've gained a deeper appreciation for the wonders of quantum mechanics. Until next time, keep exploring, keep asking questions, and keep diving deep.